Hi. So in this talk we are going to discuss about KVM hypervisors on ARM systems. As you know, the KVM hypervisors are the part of Linux kernel, and so they are automatically available to the devices in which Linux kernel is running. And we know that Linux is running in all sorts of devices, from air traffic control system to self-driving cars to the home appliances that we have at home. So it may be possible that some of the devices around us will have KVM enabled on it as well. So in this talk we will talk about the security flaw using which it is possible for an attacker to gain a privilege on hypervisor that is running with a more privileged level from a less privileged kernel mode. So before I start my talk, I would like to introduce myself. So I work for Samsung Research America, and before joining Samsung Research America, I worked for various other companies like McAfee, Citrix, and Bromium. And I worked in various areas of security like vulnerability research, secure SDLC, and also I have architected and developed a malware detection engine for Bromium. So right now I'm actively working on ARM system security, and so this paper is one of my research on ARM system security. And the opinion that I'm sharing with this paper is my personal opinion, and it may not represent the opinion of my employer, just a disclaimer. So just to give you some background about this flaw, so I found this flaw early this year while doing some research on ARM hypervisors. So and on 25th January I reported this issue to Red Hat product security team, and with that I provided them a complete detailed report and exploit code. And after that we had multiple email exchanges, and I helped them understanding the problem, and finally they understood the problem, and after that they escalated that to the KVM team. But this flaw is still not fixed, so I decided to submit a Black Hat paper, and thanks to Black Hat for providing me a platform to share my research. Okay, so I will start with the basic ARM V8A architecture. So as we know, in ARM V8A there are 4 exception levels, and program executes in one of these 4 exception levels. So exception levels determines the privilege level. Higher the exception value, more privilege it has. So hypervisor running in EL2 will have more privilege than the guest OS that is running in EL1. So if the OS wants to request some service from hypervisor, for that there is a special instruction called HVC, that is hypervisor call. When these instructions are executed, they result into a synchronous exception, and these exceptions are handled by the hypervisor. The hypervisor has the handler code in it, and through that exception handler, hypervisor services the request back. So this is how secure communication happens between OS and hypervisor. And so the moment any exception occurs, CPU executes its corresponding handler code. So the location where these handler codes are stored are called exception vectors, and these vectors are stored in a special table called exception vector table. And every exception level has its own vector table. So EL1 will have its own, EL2 will have its own, and similarly EL3. So in this talk we will just talk about EL2 exception vector table, because we are just talking about hypervisors. So, and the base address of these exception vector tables are stored in a special register called VBAR registers. And these VBAR, each EL has its own VBAR register as well that points to the corresponding exception vector table for that particular EL. So VBAR EL2 will point to exception vector table of EL2, and this exception vector table has 16 handlers in it, and each handlers are executed based on the kind of exception. So in case of HVC that is originating from 64-bit kernel, the exception handler that will be executed will be at an offset of 0x400. So when HVC is originated from 64-bit kernel, CPU refers to this VBAR EL2 register, obtains the pointer, then it adds 0x400 to it, and then executes the handler code from there. And this is how hypervisor services the request to the OS, and they communicate with each other. So this explains us between how the internally how the communication happens between the OS and the hypervisors. Now we will see the hypervisors on ARM. So in order to support virtualization in ARM, hypervisor has to execute in EL2. And this is needed because in order to access the hardware that is needed to support virtualization, a software can access those hardware from EL2. So that's why a hypervisor has to execute in EL2. Some portion of it has to be present in the EL2. And there are two kinds of hypervisors, type 1 hypervisors and type 2 hypervisors. So type 1 hypervisors are the bare metal hypervisors, and the host is considered as a VM in that. So that is the main difference between type 1 and type 2. So host is considered as a VM, and Zen is a classic example of type 1 hypervisor, and it runs completely in EL2 on ARM. And type 2 hypervisors are the extension of the host kernel. So that's why the host kernel is not considered as a VM in that. And KVM is a type 2 hypervisor. And KVM runs partially in EL2. So for ARM, KVM has two components, a low visor and a high visor. Low visor runs in EL2, and this is the core guy, and it does the configuration of the hardware and the VM switching. So this component does the low level stuff, and the high visor runs with the Linux kernel, and it uses the resources that are provided by the Linux kernel. Okay. So in order to support KVM in Linux, so Linux has to boot in EL2. So one of the initial thing that Linux does when it starts to boot is it checks the current EL value, the exception level value. So if the exception level value is 2, then it knows that, okay, I'm running in EL2, so I can access vbar EL2 register, because vbar EL2 register can't be accessed from the EL1 directly. It can't be accessible from EL1. So now if Linux knows that it is running in EL2, so it can access vbar EL2 register. So it updates the vbar EL2 register and makes sure that it points to stuff vector table. We will discuss about what this stuff vector table is. So and after updating that, it switches back to EL1 and normal boot flow happens. So what it is doing is that it is registering stuff vector table as an exception vector table for EL2. And after that, normal boot flow happens. And it is very common practice to start Linux in EL2 if the processor supports that mode. As you can see, this code has been taken from the ARM trusted firmware repo, and this is for the Raspberry Pi device. As you can see, the control is transferred into EL2 for these devices, because they support that mode. And the chances are high that Linux will start in EL2, and so the stuff vector table will be installed and KVM will be enabled. So let's go inside the stuff vector table. So this is standard vector table. It has 16 entry, as we discussed in the vector table slide. And the handler that will be called will be EL1_sync. So this handler will be called when HVC will be executed by 64-bit kernel. So if we'll go inside this handler function, we will see that this processes 3 commands based on the X0 register value. So if X0 register value is 0, then it updates the vbar EL2 register with the value that has been passed in X1 register. So what this means is that once this stuff vector table is installed as an exception vector table for EL2, it provides an interface using which a software running in EL1 can update vbar EL2 register and install another exception vector table for EL2. So we will see all this with the state diagram to make things more clear. So Linux started, and it started in EL2. So it updates the vbar EL2 register and make sure that vbar EL2 register points to the stuff vector table. And after that, stuff vector table provides an interface using which it is possible to update a vbar EL2 register and register a new exception vector table for EL2. So using this interface, Linux installs the actual KVM vector table. So this is the actual KVM vector table. This will be installed in a machine in which KVM is running. And in between these two, a lot of things happens, but that is out of scope of this talk. So once the KVM is running, this vector table will be installed. We will go inside the HVC handler of this KVM vector table. So this is the handler of HVC handler of the KVM vector table. So the very first thing this handler function is doing is that it is checking from where the call has originated, whether it has originated from the host kernel or from the guest kernel. So and this check is very important, that's why the privilege escalation is not possible from the guest kernel. So the moment when it finds that the HVC is from the host kernel, then the control goes down and it checks the value of X0 register, whether it is less than 3 or not. And if it is less than 3, then it calls another function called _KVM handle stub HVC. So if you will go inside this function, we will see that there is a command called HVC reset vector command. And with this command, if the X0 value is 2, with this command, it disables the memory management unit of EL2. And after disabling the memory management unit of EL2, it installs the stub vector back into the system. So what this means is that now stub vector table is back into the system, and stub vector table provides an interface using which it is possible to install another exception vector table for EL2. So attacker can use this interface to install an attacker exception vector table. So we will see with the state diagram. So now KVM is running, and the KVM vector table provides an interface called HVC reset vector interface, and if that HVC is originated from the host kernel, then the vbar EL2 will point to the stub vector table, and stub vector table will be registered as an exception vector table. And this stub vector table we already discussed that it provides an interface using which another vector table can be registered. So attacker will register its own exception vector table and get control over the EL2. So now we will see with how the attacker will exploit this in order to get code execution in EL2 from host EL1. And this will explain things more clearly. So in order to execute code from host EL1 to EL2, attacker will first load the value 2 into X0 register. That means attacker wants to send HVC reset vector command. It wants to reset the stub vector table back into the system. And then it will execute HVC. This HVC will be handled by the KVM vector table, because KVM vector table is registered as an exception vector table. And the handler of the KVM vector table will disable the memory management unit of EL2. And after disabling the memory management unit of EL2, it will install the stub vector table back into the system. So now a stub vector table is back in action. After this, attacker will allocate a physical continuous memory. Here physical continuous memory is needed because the memory management unit of EL2 has been disabled, and attacker wants to allocate a physical continuous memory, and it wants to register that physical continuous memory as an exception vector table for EL2. And then attacker will embed a shellcode at an offset of 0x400. 0x400 because the exception handler is at this particular address. Then attacker will load the value 0 into X0 register, and then the physical address will be loaded in X1 register. And again HVC will be called after these 4 steps. This HVC will be handled by the stub vector table, because now stub vector table is back into action. And the handler of stub vector table will install the attacker allocated buffer as an exception vector table for EL2. And after that, once this is done and the shellcode is at an offset of 0x400, so attacker need to execute another just as HVC call, and game over. So attacker is able to execute code in EL2. So after providing this much of detail to KVM team and the Linux team, I got this reply from them. So based on their reply, it seems like their threat model assumption is the code that is running in the host EL1 is equivalent to the code that is running in EL2. And that's why they don't care about the privilege host that they have added into the isolation boundary. And they don't think that this is a security issue at all, that's why. And they think that if host kernel is compromised, game is already over. But in practice, EL1 is not equal to EL2. And EL1 has a lot more code running than EL2. EL1 has wider attack vector than EL2 because it is interacting to outside world. It may have some custom driver running in it. So EL1 has a lot more attack vector as compared to EL2. EL2 is running in a lot more closed environment. The interaction is very closed for EL2. It's a hypervisor. So what they think as an end of game can be a beginning of a new game for an attacker. So if I'm an attacker and if I manage to get into the host EL1, the first thing that I will do is that I will exploit this design and I will migrate my attack into EL2. And once I migrated my attack into EL2, I will make sure that my attack is isolated by configuring stage 2 page table, so that the code that is the memory scanner that is running in EL1 will not be able to see my code. And so that will make my code very stealthy in nature. It will be hard to detect my attack. After doing that, I can also configure EL2 in a lot of different ways to make sure that I'm getting the control from various different places, like configuring interrupts and all. And EL1 will not even know about it. And the third thing is that I can use this to bypass a lot of the protection mechanisms that are implemented in the kernel, like patch guard or Linux runtime guard, in a generic way by directly escaping into EL2. And fourth is that if somebody has implemented some secure monitoring software in hypervisor using KVM, something, say they have custom implementation, so attacker can attack those things as well. Because now attacker is able to execute code in EL2. So seeing all this point, it seems like it can be a very juicy target for an attacker to perform a very sophisticated and stealth attack, which will be hard to detect, like Blue Pill on ARM. And this design has a bigger impact on mobile and IoT because most of them runs on ARM, and the chances are high that they will start in EL2, because if the processor support that mode, then it starts in EL2, and they are single kernel devices, so they have wider attack surface, because it may they will interact to outside world, and may possible that they have some custom driver running in it. So they are more impacted by this, and the affected architecture is ARM v7A and ARM v8A with hardware virtualization. So this describes the security problem and its implications. So if you think that your system is vulnerable to this, patch your bootloader and make sure that your Linux starts in EL1 and your KVM is disabled by default, and that will ensure that the attacker will not be able to use Linux as a backdoor to install another hypervisor-based rootkit into your system. So I have a demo which I would like to show that using this, it is possible to execute code from host EL1 to EL2. So for that, I'm using QEMU and I'm running ARM machine using QEMU. So I've started my QEMU machine. So it has Cortex A57 processor running in it. Now I attached a GDB to that my ARM machine and continued the so now Linux is starting. Now I will check the version of Linux. So it's a recent version that I'm running. I just rebased a few weeks back. Now I will add few breakpoints here. I will put breakpoints in reset vector and set vector call. So my exploit code will call this reset vector. First it will call the reset vector to reset the vector table as a stub vector table, and after that it will call set vector table. So now I'm running the exploit test program that will call reset vector first. So now this will set the stub vector back into action. And now it will call the set vector table so that attacker allocated buffer will be registered as an exception vector table for EL2. So it will pass the buffer address as well. So here the set vector has been called, and X1 register will contain the physical address of the attacker allocated buffer. So GDB is not able to access it because this is a physical address. So now we are putting a breakpoint at an offset of 0x400 from this buffer. So because our shellcode is at this particular offset. So the moment our shellcode will get code control, the breakpoint will hit. So here we get the execution. So now our shellcode has started executing. So now we will go in assembly view. And this is our shellcode. So the very first 3 statement, we are just fetching the value of the current EL and storing it in X1 register, and then we will print the X1 register value to see in which EL my shellcode is running. So as you can see, the X1 register has value 2, so that means shellcode is running in EL2. And now what I will do, my shellcode will read all the EL2 registers and send the information back to the EL1. So we are able to access the hardware register of EL2 from EL1. So as you can see, we are able to access all the hardware register of EL2 from EL1. So I think this concludes the talk, and so in order to mitigate this problem, we need to patch the system so that by default the KVM is not enabled in the system, and the system is not vulnerable against the hypervisor based rootkit. Thank you. Any questions?